wonderful, we will see wonderful ideas, and we will face with challenging problems. And this is really an exciting topic. So I'm very happy about that.
Okay. All right. So thanks, Avishai. Somebody reminded us on chat, I think, that we weren't recording the lecture. So I just started the recording. People who are joining this late or offline may miss the first few minutes. So I'll try to recap it at some point. Okay. So maybe now that Avishai has introduced himself, I should do the same. I'm Umesh Vazirani. I've been, I think I've been here forever. It's for too long for me to remember. My interests are in, well, okay, so my current interests are mostly in quantum computing, although I've worked a lot in algorithms in the past and in complexity and so on, various subjects. So, so, I hope that during this this course, we'll give you a little bit of a taste of quantum algorithms right at the end of the semester. So that'll be something to that'll connect with something. Okay, so let's see. I also wanted to let me repeat a little bit about the lecture format. So we are going to be doing these short pre-recorded videos, at least for the first few lectures, to see how well it works out. And then after each of these pre-recorded videos, we'll have we'll stop for a discussion. In terms of the questions and answers, and during these question and answers, I'd request that you actually start your video and unmute yourself so that you can speak. And so we'll try to have as normal a discussion as we can. We'll try to pretend we are in the same lecture room. In terms of discussion sections, also, what we understood from last semester is that there was not that much engagement, and so again we are going to try something new. What we'll try is that beginning of the week, you'll get a pre-recorded discussion video with a mini lecture and maybe a brief working through of the discussion sheet so that you understand what the discussion sheet is about. In the middle of the week, there'll be live discussion sections that you can go to, and in those discussion sections there'll be a TA, but also tutors, so that you have some you can be in small groups and interact in small groups. And then towards the end of the week, there'll be 2 more videos released. One which might summarize some of the most frequently asked questions in the live discussions and office hours, as well as some of the most interesting questions asked in those discussions and office hours. And then there would be one more video which would be a walkthrough, walking you through the solutions. Okay, so it's an attempt to try to capture this, to make sure that there are some parts that you can just do on your own through recorded videos, and some parts where you engage. And the philosophy is that when you engage as intensely as possible. So, in shorter bursts. So it's a theory. We'll see how well it works, and we'd like to hear your feedback once we get going, whether you like the way it is and whether it's working out for you. Okay. Now there's one other thing that that we were going to slightly change compared to last time, which is on the homeworks. So one feeling is that possibly some of the the homeworks are either throwaway questions, too simple, or much of it is very hard, and then you have to you're of course encouraged to collaborate with other people, and this is where a lot of the learning actually happens. But Possibly what's missing is these intermediate questions that you can work on by yourself, but they're not throwaway questions. And so we'll try to add these in the homework, and those will be designated as such so that you would actually be the instructions on those would be that you do not collaborate with anybody. Okay, so I think the main reason to do this is that if you are collaborating on the homework, on all the homework, then it's easy to get uncalibrated, where you feel that you understood everything, but then when you try to do it by yourself, it's hard, right? So this way you get to do a few questions by yourself, and they're not that hard. So you get calibrated. Are you actually understanding things as you go along? Okay. Maybe this is a good time for me to stop and ask if there are any questions.
I actually do have a question. For the solo questions on the homework, yes. Will we be able to ask questions to the TA, for example? Is the TA going to be able to help us?
I would imagine the TAs can always help you. The question is how much they should help you, and we'll sort this out as we go along. Okay. I think that basically, all these policies, we are trying to figure out what would help everybody the most. So as we introduce these policies, we'll try to sort this out. So, okay. So I should mention that we have a absolutely wonderful staff of TAs and tutors and readers. You would not imagine the amount of time that went into assembling this team. I think that they'll be present in the next lecture, and we'll spend some time doing introductions in the next lecture. So, all right. Any other questions?
CS170 last semester had a policy where you could redo missed homework questions for some partial credit. Will 170 be offering that this semester or not?
That's not the plan. We'll certainly consider it, but I think that we had done that in the past, in CS70, and it, I had actually, okay, so just to say, a few years ago, I had really instituted that in a much bigger way in CS70, and I didn't think that it worked out so well in terms of the student experience. So, I'm again open to anything, but I'd like to make sure that whatever we are doing is actually helpful and not too complicated for everybody. Yeah, any other questions? Okay, so here's so what I'm going to do now is I'm going to share the first video, and then after watching it, we can go ahead and do a session, some discussion. All right, so let me see how to start this. Okay, so let's share the screen. Welcome to algorithms. It's a wonderful subject that has shaped the world we live in profound ways. And in this course, we'll talk about some of these great algorithms. And I hope that as we talk about them, we are able to convey to you some of the beauty and the elegance and the power of these algorithms. You might also wonder sometimes about how anybody thought about these algorithms in the first place. The other thing that we'll do is talk about the design principles behind algorithms so that you can learn how to design algorithms by yourselves. Okay, so I'll speak a little bit more about this later in this lecture, but I want to start by talking about the simplest questions about algorithms, such as, what's an algorithm? Or possibly, what's the difference between an algorithm and a program? So one way to answer this question is by an analogy. So algorithms relate to programs in much the same way as a sketch relates to a photograph. So there are a lot of similarities between algorithms and programs, but there are also some key differences. So you might you might think that a photograph is in every way superior to a sketch because, after all, it's full of details and it's much more lifelike. But there are some things that a sketch can convey or do for you that a photograph may not. So in a sketch, you can actually highlight certain aspects. A sketch can give you insights into underlying mechanisms. And a sketch is also much more lightweight, and it can help you explore much more easily the various possibilities. So for example, an architect might, typically will draw sketches, and that has all these benefits, in terms of designing and so on. So there's another way of expressing this advantage of a sketch or of an algorithm, which is abstraction. And we will see that this notion of abstraction comes into algorithm design in multiple ways. And the best way of seeing this is by a simple example. Okay, so the example we look at is Fibonacci numbers. So I'm sure you all know about the Fibonacci sequence. It goes 0, 1, 1, 2, 3, 5, 8, 13, 21, 34. And the way this sequence is defined is by saying f sub 0 is 0, f sub 1 is 1, and fn is fn minus 1 plus fn minus 2 for n greater than or equal to 2. Okay, so now these Fibonacci numbers grow very, very quickly. And so you might want to compute something like, what's f200? What's the 200th Fibonacci number? And so it's natural to just write a program to compute the Fibonacci numbers. And so what you'd write is something like, well, function fib n. If n equal to 0, return 0. If n equal to 1, return 1. Otherwise, return fib n minus 1 plus fib n minus 2. Now, notice to begin with that what we wrote here is not code that can actually be run on any machine. This is called pseudocode. Okay, what the pseudocode is meant to do is actually explain the algorithm to another human. And so we try to make it as simple as possible, and just to try to convey the main idea. So that's one way in which an algorithm is more like a sketch. Okay, so now once we write such an algorithm down, there are three questions we ask about it. The first question is it correct? And again, the fact that we write out this algorithm as pseudocode actually helps us in proving that the algorithm that we've written out is actually correct. So again, you might think to yourself, you can do even more and actually write out a program for computing, this function. And in fact, sometimes less is more. So writing simple pseudocode is worth more than writing out the full program that you can actually execute. In this case, the answer, is it correct, is obviously yes. And the reason it's yes is because, well, we just followed the definition of the Fibonacci numbers. The second question we might ask is, how much time or how many steps does it take as a function of n? And okay, so to understand this, we let t of n be the number of steps taken by this algorithm on input n. So it should be clear that t of 0 and t of 1 are both small. They are at most 2, right? Because you check one condition or another condition and then you answer. And t of n is t of n minus 1 plus t of n minus 2 plus, well, 1, 2, you have to do an addition and you have to do some other steps. So let's say 3 steps if n is greater than or equal to 2. Now, if you look at this function t of n, it looks remarkably close to the definition of f of n. And in fact, it only seems larger. So what we can say is that t of n must be larger than f sub n, the nth Fibonacci number. But on the other hand, here's a simple claim about the Fibonacci numbers. The nth Fibonacci number is at least 2 to the n over 2 minus 1 for n greater than 0. Okay, so this is something that you can prove. It's a nice exercise. Or, if you want an even more accurate bound, you can sort of say f of n grows roughly as 2 to the 0.7 n. Okay. So let's see what this says about how long it would take to actually run such an algorithm on a computer. Well, the fact that this is exponential time, it's worth trying to understand just how bad exponential time is. So to understand that, let's just try to look at how exponential time relates to, how it quickly becomes astronomical. So let's look at how long the universe has existed. So the age of the universe is about 13 billion years. Okay. Which is about 10 to the 10 years. Now, if you write it down in seconds, then it's about 10 to the 19 seconds. And if you were to use a very fast computer, say 100 gigahertz, then that's like 10 to the 30 cycles, or 10 to the 30 cycles, or 10 to the 30 steps or instructions. And then if you convert it to base 2, you'd get 2 to the 100, roughly 2 to the 100 steps. Okay. What this means is, if you combine this fact with this claim, and the fact that we are trying to compute the 200th Fibonacci number. So to compute the 200th Fibonacci number, this particular algorithm would take about 2 to the 100 steps. And 2 to the 100 steps would take us about the age of the universe on a fast computer. Okay. So this is really not a good algorithm at all. Now, why is this not a good algorithm? Well, here's a way to understand it. I hope you've already seen this, so this may be a bit of review for you, but let's just do it anyway. So when we call Fibonacci on n, it recursively calls Fibonacci on n minus 1 and n minus 2. These in turn recursively call n minus 2, n minus 3, n minus 3, n minus 4, and then we can keep going. This gives us n minus 2, n minus n minus n minus 4, n minus 5, n minus 4, right? And you start seeing that we are computing the same quantities over and over and over again. That is the same quantity as that, is the same quantity as that. This is the same quantity as this one, and so on. And so this is what leads to this terrible inefficiency in computation that we are doing. Okay, so how should we do this? Well, there are two ways of getting around this. One is we could memorize, which means the first time we compute, we execute Fibonacci on n minus 4. We remember the result, and the next time we try to compute it, we just look it up. Okay, and that's sort of the answer to the third question we ask about algorithms, which is, can we do better? And in this case, the answer is yes, we can do better just by memorization. But in fact, there's another way we can write out this function, and write a nicer, a cleaner algorithm just by saying, let's write out Fibonacci of n. What we do is define an array f from 0 to n, and we define f of 0 equal to 1, f of 1 equal to, f of 0 equal to 0, f of 1 equal to 1, and then for I equal to 2 to n, we let f of I equal to f of I minus 1 plus f of I minus 2, and then we return f of n. So again, we can ask the same questions. Is it correct? Well, again, the answer is yes. It's just, we just followed the definition of the Fibonacci numbers. How long as a function of n? So if you compute the running time, then we can see that the inner loop, each time through the inner loop, we just have to do a single operation, a single addition. So it takes a number of steps which is linear in n. So it takes a number of steps which is proportional to n. And the way we write that down is big O of n. It's bounded by some constant times n, 2 times n, 3 times n, something like that. And then we can again ask the third question, can we do better? Such as, what's an okay, so time for discussion. Any questions about that?
Sorry to bother you, Professor, but the video quality was rather pixelated, so it was hard to read what was on the screen.
Oh gosh.
Yeah, I know I wasn't the only person who had this issue, so if you don't mind, could you link the videos in the chat so we could like watch them individually?
Yes. Let's do that. So I'll do that for the next video immediately, and then yeah. We were thinking about how it would be best to deal with this, but okay, I'm going to share with you the 3 videos that are part of this, that form this lecture. Oh, what happened here? Okay, so I'm just so I just sent the links to everybody, so you can you know, there are 3 videos. We just watched the first one. Okay, so so let me just say a little bit about that video. I hope this was all really familiar to everybody. I hope you've all seen Fibonacci numbers and how to compute them. So the point of this was not computing the Fibonacci numbers, but exploring, you know, what an algorithm is, and you know, how you should think about it. You know, should you be writing pseudocode? How do you analyze it? What are the questions you think about when you think about algorithms? Any more? Yeah, you can ask questions by unmuting. You know, right now, since we don't have too many questions, so you can just speak up if you have a question. If you have a lot of them, then you could raise your hands and and I can call on you. But right now, if anybody has a question, just speak up.
I was wondering, when we're following a definition and implementing an algorithm, how can we like double check that we didn't like misinterpret the definition itself? And so we would think that we are following definition, but in fact we're not.
Yeah. You know, okay, so you know that there's a trade-off, right? Eventually, a proof is supposed to be something which is, which is just, broken down into such small steps that it can even be checked by a computer, right? That's the ultimate proof. But it's also the ultimately, opaque proof, because you look at it and you just see this blur in front of you. So there's a trade-off, and what we do in this course is we sort of stay towards we err on the side of humanly understandable proofs. So from our point of view, a proof is an idea. Once you understand the main idea, then it's a matter of translating that into a more formal proof, and we sort of assume either you already know how to do it, in which case we don't want to belabor the point, or if you don't know how to do it, this is not the course in which to teach that, right? So it might be there's a better chance that you will be able to understand these algorithms at the level of what's the main idea, than use this class to understand how to translate that into a formal proof. So it seems like a good trade-off to assume that if we treat this at this high level and just try to polish and clarify what's the main idea, that's going to be the most effective way to reach as many people as possible.
Okay, thank you.
Any other questions?
Could you, do you mind going over again? You said something like the pseudocode is different than the algorithm, but it's also different than the actual code. Like, what is the difference between the pseudocode and the algorithm?
Oh no, so I said, sorry, maybe I'm not sure if I said that. So what I meant to say is that the pseudocode is a way to convey the algorithm. You take the essential ideas of the algorithm and you write them down precisely in terms of the pseudocode.
Okay, thank you.
Okay. Any other questions? Okay. Anything else?
I had a question about improving an algorithm.
Mm-hmm.
So when you ask the question, can we do better? Like, what are some of the things you would look at to try to identify how to improve an algorithm? Okay, that's a very good lead up to the next video, which is how do we improve this algorithm even further? Okay, so but before we get there, let me just make sure there aren't other questions, because then we'll move on to how to improve even further. Okay. Anybody else?
Yes. Will future pre-recorded videos be uploaded to Piazza like right before lecture or like a day before lecture?
Yeah. So we'll try to upload them before the lecture. Certainly. So I think we're going to try this experiment out for a few lectures, and then if it I think the fact that some of you could not found the video to be grainy when it was being broadcast like this. My guess is that means if we were to do a live lecture, that might also be grainy, so it might be an indication that we should pre-record. But I'm certainly very open to either doing live or pre-recorded, and we'll see how it goes. So certainly, if you have feedback on this, please do provide it. Maybe we can do a Piazza poll or something.
Hi, Professor. I have a question. I was wondering if we are just going to watch pre-recorded videos in the lecture, or are there parts of the lecture that are not covered in the videos?
So right now the format is, there'd be a pre-recorded lecture together with this live discussion, but I'm certainly happy to reconsider that depending upon what the experience is. Great.
All right, thanks.
Okay. So let's go on to the next lecture. Okay. So we'll try to. Okay. So again, I'm going to go ahead and do a screen share. But of course, you are welcome to just watch it on YouTube directly. Okay.
Professor, for this one, it might be worth trying just sharing the audio as you were sharing it before, where it was playing out of your speaker, because the video quality was fine at that point.
Okay, so in other words, I should not click the special video sharing, right? And
yeah, you shouldn't share audio from the same the computer you're using to screen share.
So don't share computer audio, but optimize screen share for video clip?
Yeah.
Okay, let's try that.
Wait, aren't we going to want the audio?
So the audio will play out of the speakers and then through whatever the professor is using right now to speak. Yeah.
Okay, so let me try that setting. Okay, so let's see if this works. And this is something that we'll see in the next lecture. Oops, sorry. Algorithm. Okay, so to try to understand this, let's write out f of n equal to f of n minus 1 plus f of n minus 2 in slightly different notation. So let's write a vector which looks like this: f n minus 1, f n minus 2. Okay, so we just write out a vector with 2 entries. And now let's write out a matrix whose a 2 by 2 matrix whose first row looks like 1, 1. And so if you look at this first entry here, it's actually going to be just f sub n minus 1 plus f sub n minus 2, because the way you multiply this matrix times a vector is you take the first row and you multiply the first entry by the first entry, second entry by the second entry, and you add them together. So you get f sub n here. And now just for symmetry, what we'll do is we'll make the second row of the matrix 1, 0. So now this entry is just going to be, you take this row and you multiply by this column. So you get 1 times f of n minus 1 plus 0 times f of n minus 2. So this just gives us f n minus 1. So what we've done is, when we multiply f sub n this vector by this matrix, we just advance the Fibonacci numbers by 1 index. Okay, so here's an example. So if we start off with n equal to 2, then we have f sub 0, f sub 1, and then we multiply by this, and we get answers 1, 1. right? And now what happens if you multiply 1, 1 times okay, again, we get to the next pair of Fibonacci numbers. So we move by 1, so we get 2, 1. Okay, so now what's the point of all this? Well, we could also now say, well, this is further equal to, so if you were to write f of n minus 1, f of n minus 2, we could write it as just multiplying this matrix times f of n minus 2, f of n minus 3. And we could keep unwinding this one at a time until we get, this is the same thing as taking this matrix 1, 1, 1, 0 and multiply it by itself n minus 1 times. And then we get all the way down to 1, 0. Right? So I'm just unwinding. I'm going from f of n minus 1 to n minus 1, n minus 2, n minus 2, n minus 3, all the way down to f of 1, f of 0. Okay. So if we want to compute the nth Fibonacci number, all we have to do is take this matrix and multiply it by itself n minus 1 times, and then multiplied by this vector. Okay, and so so let's see how hard that is. Okay, so if we were to take this matrix and if we were to multiply it by itself, what would we get? Well, we'd get again one, this top left corner is this vector times that one, so it's 1 times 1 plus 1 times 1, that's 2. This entry is 1 times 1 plus 1 times 0, so that's 1. Similarly, 1. And then what's this entry? That's 1 times 1 plus 0 times 0, which is again 1. Okay, so now suppose we wanted to multiply this by itself 4 times. So if you wanted to raise 1, 1, 1, 0, whole raised to power 4. Well, this is the same thing as multiplying 2, 1, 1, 1, and multiplying it by itself twice, because each of these is already multiplying 2 of those. And so if we do that, so we just write 2, 1, 1, 1 times 2, 1, 1, 1. And what do you get? Well, you get 2 times 2 plus 1 times 1, 5. 2 times 1 plus 1 times 1, 3. 3, and then 1 times 1 plus 1 times 1 is 2. Okay, so now what does it take to multiply this matrix by itself 8 times? Well, we already have the matrix multiplied by itself 4 times. That's this. So all we have to do is take this matrix, 5, 3, 3, 2, and multiply it by itself like that. And so what do we get? Well, 5 5s are 25, plus 9 is 34. 15 plus 6 is 21. 15 plus 6 is 21. And 3 times 3 plus 2 times 2 is 13. Okay. And we can keep going this way until we get to matrix to the power of n, or n minus 1. So how many multiplications do we have to do? Well, each time we are doubling the exponent, and we want to only get up to n. So we just need to do log n matrix multiplications. But how hard is it to do this matrix multiplication? Well, as you can see, each matrix consists of only 4 numbers. And the way you multiply these 4 numbers is, well, for each of these numbers that you get as a result, you have to multiply, do 2 multiplications and 1 addition. So it's 3 operations per entry that we are calculating. So there are 4 entries to calculate. So, and each matrix multiplication takes 12 operations. Right? 12 operations of multiplications and additions of numbers. So the total number of operations required to compute this matrix, and then what do you do? Well, then f sub n is just the top left entry, right? So then you'll multiply by 1, 0, 1, 0, and so this 1 will multiply that. So that's going to be f of n. So what's the total running time of this algorithm? So the number of steps is just 12 times log n. So look at what happened. We started off with an algorithm that took an amount of time which went at least as large, which was at least as large as 2 to the n. So we went down from 2 to the, say, n over 2. From that, we decreased to order n. And now we've decreased to order log n, right? So this was, n was exponentially smaller than this number, and log n is exponentially smaller than n. Seems like we've done really well for ourselves. There's a problem though with this algorithm. The problem is that here we are assuming that when we multiply 2 numbers, it just takes 1 step. But see, these numbers are growing very, very quickly. In fact, the nth Fibonacci number, which is what we're trying to compute, it is roughly n bits long, or it's n over 2 bits long. So when you're multiplying 2 n over 2 bit numbers, that's not a unit step operation on your computer. What's a unit step on your computer is multiplying 2 8-bit numbers, or 32-bit numbers, or 64-bit numbers, but not 200-bit numbers or 1,000,000-bit numbers. So actually, once you look at this more carefully, the running time of this algorithm is not log n steps, but it is dominated by it's the number of steps to multiply 2 n-bit numbers. And the question then becomes, how fast is that? Actually, now that we are doing this, we may as well go back and fix something that we said before. What we said is that this previous algorithm that we wrote down takes order n steps to compute. But actually, it doesn't take order n steps, because you see, the step that we said, the inner loop, we go through this inner loop n times, and each step in there is just an addition. But what we are doing is, in general, we are adding long numbers. F of I is roughly I bits long. And so the amount of time required to do this, to add 2 I-bit numbers. So when you're doing addition, so if you're adding in binary 1 1 0 0 1 1 0 1 1 0, well, what you have to do is, well, you do the addition bitwise, sometimes with carries. So you have a carry like that. And so the amount of time it takes to add two n-bit numbers is itself order n. And so when you work through how much time it takes to do all these additions, well, initially, it'll take you rough on average n steps to do one of these additions. And there are n such additions. So the amount of the running time of this algorithm will not be order n, it'll actually be order n squared. So now we can go back and we can say, well, the number of steps of our three algorithms, the first one was exponential in n, the second was polynomial in n, was order n squared. And the third one is not actually order log n, it's actually dominated by the number of steps to multiply two n-bit numbers. And so whether this third algorithm is faster than the second algorithm or not depends upon whether we can multiply two n-bit numbers faster than n squared steps. And this is something that we'll see in the next lecture. Okay, so any questions about that?
It's like I know is multiplication is definitely harder than addition. As you demonstrated, addition already takes like order n times to finish, like in terms of like big N. So how is multiplication done in like bitwise? I'm just like a little bit curious about it.
Oh yeah, so we'll talk about that in the next lecture. So we'll talk about exactly how long multiplication takes and how one can speed it up and so on. So this is, yeah, it's exactly
okay.
what we've been
Thank you very much.
I had a question about when it's legal to do like this matrix multiplication sort of out of order. I thought that you couldn't do matrix multiplication like this, but is it always valid to do matrix multiplication?
Oh, that's a very good question. So here with matrix multiplication, it's not like you're right. It doesn't act like normal multiplication, and specifically, oops, yeah. Okay, specifically, the way it does not work like normal multiplication is that if you have two matrices A and B, then A times B is not the same as B times A, right? If you have two numbers, A times B is the same as B times A. With matrices, it's not true. Okay, so I mean, the thing you think about is rotations. If you rotate about one axis and then another, it's not the same as rotating about the second axis and then the first. Okay, but here what we were doing was we were multiplying several matrices with each other. And there the question is, if you have A times B times C, in which order should you do the multiplication? If you do A times B and then multiply by C, is that the same as multiplying B times C and then pre-multiplying by A? Can you do it in different orders, right? How do you put the parentheses? It turns out matrix multiplication is associative, just like numbers.
Okay, thank you.
So that's what we.
Professor,
Oops, sorry, go ahead. Sorry, can you unmute yourself?
I was just gonna ask, why is like the nth call to fib in an n-bit number? I thought it was supposed to like a number n should have log n bits. Is that wrong?
No, because the nth nth Fibonacci number is roughly 2 to the n over 2.
Okay.
Somewhere between 2 to the n over 2 and 2 to the n.
Okay.
It has somewhere between n over 2 and n bits.
A quick question about the algorithm that claimed to originally have log n runtime. You mentioned that it was dominated by the amount of time it takes to do multiplication, which was n squared. Like, so what is the actual runtime of the algorithm, or is it kind of unclear?
Well, the actual runtime depends upon what kind of algorithm you're using to multiply numbers. So if you use a naive algorithm, then it'll take n squared steps. But can you do better than that? Well, we'll see, right?
Okay, I see.
That's
Professor, I was confused about why it would just be log n, because if we had like an odd number, some number that was like 2 to the n minus 1, then wouldn't we have to consider all those steps leading up to log n? Like it wouldn't just be purely log n?
Yeah, it wouldn't be log n. It would actually be something like 2 log n. Right? So, and if you're writing in big O notation, we don't care. So you know, it would be, you know, let's say that n minus 1 was not a power of 2, but it was you know, it was almost a power of 2. It was 2 to the k plus 2 to the k minus 1. So then you'd keep multiplying, you'd get to 2 to the k minus 1. Then you'd multiply again, you'd get to 2 to the k, and now you'd multiply 2 to the k times 2 to the k minus 1 to get the final answer. So it's not too bad. Okay, it's something that you can.
Thank you.
When we get a question like this, what can we assume about the ISA? Like, do we assume that 8-bit additions, subtractions, multiplications are constant? And like, what else would be constant?
Yeah, so first let me answer, you know, that's a really good question, but let me answer it not as a question about what you should do in an exam, but how would you treat it in real life, right? So the whole thing we are trying to do when we are studying algorithms is we are trying to, you know, we are trying to abstract out, and we are trying to make life as easy for ourselves as possible, right? So it's like sketching. So we want to throw out any unnecessary details. Now, sometimes, you know, when you throw out what you think are unnecessary details, you realize actually you threw away something that was necessary. So that's what happened to us when we made up this log n time algorithm. We threw away too much, and then we had to bring it back in. So here's how we do it, you know. So there are going to be many situations where the numbers we are going to be dealing with don't get very large. So then we can assume that, you know, the numbers are small enough that they fit in a word in our machine, in our computer. So it's at most 64 bits, let's say. And since our computer gives us a way to multiply two 64-bit numbers in a single instruction, it makes sense for us to think about multiplication as a single step. Right? When we are, on the other hand, when we are computing Fibonacci numbers, or if we are trying to factorize a number or compute primality, then we are dealing with very, very large numbers. You know, they might be thousands of bits long. And now it's no longer fair to think about addition or multiplication as just being a single step. And so then we go to what's called a bit model, where all we can do in one step is we can multiply 2 bits, or we can add 2 bits. And then if you want to multiply n bits, then we have to build it up out of single bit multiplications and additions. Okay? And then it takes as long as it does as a function of n. Right? So the thing with algorithms is we have this simplified machine model. And the correct machine model is you can only do bit arithmetic in a single step. But then sometimes it'll become too cumbersome for us to keep track of all that. And since we are only going to be using small numbers anyway, we'll just say, look, additions and multiplications are a single step. It'll simplify our life for us. So what you're supposed to do, you know, that's part of algorithmic training, is you understand the situation, and it's really going to be these two different situations. There aren't going to be so many different situations. So either the numbers we have are large, and then our model has got to be, we have to keep track of exactly how long it takes to do arithmetic operations, or they are small, and then we don't care.
Professor, if you were to use the naive approach of multiplication, would the runtime of this faster matrix multiplication be n squared log n, or O of n squared log n?
I think, okay, you know, we should, let me see, would it be n squared log n, or would it just be, I think it might just be n squared, because it would be a telescoping sum. It'll be a geometric series, I think. So the log n would disappear into the n squared. Okay, it might be something like n squared plus n squared over 4 plus n squared over 8 and so on. And because of that, it'll just give you at most 2n squared or something.
Thank you.
So is the runtime O of n squared because each of the fib calls take O of n, and then we want to add it n times, so it's n times n, which is O n squared?
Yeah, it's that's right. Each of the calls takes, that's right. That's right.
Okay, thank you.
Professor, can you explain one more time if you have in relation to your log n algorithm, if you have like 2 to the k minus 1, why that is a constant times log n instead of like, since like, for example, if you have like the number 15, you gotta have to multiply the matrix corresponding to 8, the matrix corresponding to 4, the matrix corresponding to 2, and then the matrix corresponding to...
Yeah, so you know, if you're doubling at every step, if your number is 2 to the k, then you do k steps, because you'd go 1, 2, 4, 8, 16, and so on. You'd go 2 to the 0, 2 to the 1, 2 to the 2, up to 2 to the k. So there are only k steps that you have to do. So if your number is n is 2 to the k, then k is just log n.
I was asking about the case when it's like 2 to the k minus 1. So it's not a perfect time.
Okay, well, maybe that we can handle offline. Okay, because I'll have to write it down. But it's you know, if you think it through, it'll actually be order log k still. Okay.
Okay.
But
yes.
you have to think
Thanks.
it through a little bit. Yes. Yeah. Sorry. Okay, so let me go ahead and share the last video. Okay, let's do the screen share again. Okay. Okay, so now let's look at some of the ways in which algorithms have had a profound effect on the world we live in. And in some of the cases that this happens, it happens because there's some phenomenon in real life which can be modeled by a simple computational model, you know, which captures its essential features. And so then this, you know, then an algorithm actually helps you not just solve something, but also understand something about that phenomenon. Okay, so let me give you a few examples of algorithms that we'll talk about, which have had a profound effect on you know, in practice. So one of these examples is the fast Fourier transform. So this is an algorithm that allows you to take two polynomials. So say you have a polynomial a0 plus a1x plus a sub n minus 1 x to the n minus 1, something like that, times, and we want to multiply it with the polynomial b0 plus b1x plus b sub n x to the n. Okay, and well, how long should it take to do that? Well, as you can see, what you have to do is you would write this as summation over I and j of a sub I, b sub j, x to the power of I plus j. And so you have basically n squared such terms to compute. And so you think the amount of time it would take to run this algorithm would be roughly n squared. You know, so you couldn't do much better than an order n squared algorithm. Well, the FFT, the fast Fourier transform, gives you a way of solving this problem in only order n log n steps. How does it do it? It's a piece of magic. Okay, we'll go through it. We'll see. It's a brilliant algorithm. Now, you might think, well, how important can that be? You know, it's very interesting. It's intriguing that you can multiply polynomials so efficiently. But what does this actually do for us? Well, it turns out that the entire field of digital signal processing.
Oh, okay.
So is the lecture over?
Lecture's not over. There's still there's still more lecture.
Okay,
Professor?
Impromptu lecture. Let's go.
Okay. Well, okay. I will, in that case, share my screen. Okay. In that case, I will share my screen. If he's not here right now. Sorry about that, everyone. Okay. Let's go ahead. Can everyone hear me?
Yeah, we can hear you.
Okay.
Now let's look at
Can everyone hear the computer audio?
some of the ways in which algorithms
Yes.
have had a profound effect on.
Ron, you should play from 320.
From 320. Excellent. Okay. Okay, I'll do that then. Play from 320.
You could think of it as a sequence of you know, a string of length roughly 3 billion over an alphabet A, C, G, T for the 4, which stand for the 4 nucleons.
The professor's deck. Professor, can you?
Yeah, I'm sharing it again.
Okay.
From, you said 320 roughly. Algorithm. Is that right?
Mm-hmm.
Yeah, that's right.
So, being able to play music online, you know, being able to record music as digitally, play it quickly, you know, all this uses digital signal processing, and all that relies on the fact that digital signal processing takes only almost linear time instead of almost quadratic time. Okay, there's a second example which I won't go into much detail about, but these are things called horn clauses. Can you skip ahead? You know, these are clauses which say something like if X. I'm just going to skip ahead. 1990, and the challenge at that time was sequencing the genome of a human being. You know, the entire gene. Now, the genome is a string of length roughly 3 billion. So you could think of it as a sequence of you know, a string of length roughly 3 billion over an alphabet A, C, G, T for the 4, which stand for the 4 nucleic acids. And so the challenge was trying to take this extremely long string of length about 3 billion and trying to reconstruct it. And what was the, you know, if you took these long strings, what was the primitive that was allowed to them? Well, experimentally, all they could do was take these small snips and figure out what the sequence was for this small snip. And these snips could be quite small, maybe of length about 100. And so there was a big problem, once you did these experiments, how would you put them all together and reconstruct this entire long string? Especially since there were lots of repeated sequences within this long sequence. Okay, so the Human Genome Project was running well behind time, and then there was an algorithms researcher who worked on string algorithms. His name was Gene Myers. He came up with an idea that instead of doing the experiments like the biologists were doing, and then reconstructing based on whatever data they provided, coming up with an algorithm to reconstruct this 3 billion length string, he first came up with the algorithm. And he said, here's a good algorithm for this. And given this algorithm, can't we actually change the experiments that the biologists are doing a little bit so that they give us different kinds of data? And then we run this much faster algorithm, and this would speed up the entire process a lot. And so there was a company named Celera that took him up on this and actually implemented this. And it turned out that, about 10 years into the Human Genome Project, the company stepped in and ended up rapidly moving towards the sequencing of the human genome. And basically, the Federal Human Genome Project actually had to borrow some of these ideas in order to finish roughly at the same time as this technique. So the particular algorithm that Gene Myers proposed was something called shotgun sequencing. And well, we'll touch a little bit upon this, but maybe we'll talk more about the underlying sort of an underlying algorithmic approach, which is called dynamic programming. But we'll touch upon this a little bit. Here's a fourth example. The fourth example is one of the major things that's come about with the internet is these completely new kind of markets. And there's a particularly important one that that Google and other search companies run, which are called AdWords markets. It's called the AdWord auction. And it turns out that there's actually an algorithm that underlies all this. And there's a very simple model that underlies all this, which looks like this. That we are given some sort of a graph. It's a bipartite graph, meaning that there are the vertices are divided into these two sets, and all the edges in the graph go between the two sides. And what we are trying to do is we are trying to match up or pair up these vertices. So for instance, here's a way that we might pair up these vertices. In fact, we can pair up all of these vertices. But now, imagine that we have the same scenario, except that the vertices on the right only arrive one at a time. So when this vertex arrives, it reveals that those are the two edges that are adjacent to it. And what you have to do is, without seeing the rest of the graph, you have to commit whether to match this to this one, or leave it alone. And so let's say you don't have any further information, you end up matching it like this. Now the next vertex comes along, and again, it reveals what the neighbors are. And again, you have to immediately commit to whether you match it, whether you pair it up with something or not, or leave it alone. And so the algorithmic question here is, how would you do this? How would you actually do this pairing so that you do well? And what does it mean to do well in this context? So again, this is an example where formulating this problem as a computational problem and as a simple computational problem, this is where the sketching, the abstraction of the algorithm comes up. And once you create such an abstraction, it actually gives you a very effective way of carrying out these kinds of options or to implement these kinds of markets. Now, let me actually go ahead and talk about two other examples that we'll talk about. There's going to be more, but I'll just limit it to two more examples. The fifth example is primality testing. This is something that you may have heard about. You're given some number n. It's a very long number. Let's say it's 1,000 bits long, or it may be 5,000 bits long, and you want to test whether n is prime. It turns out that there's a very fast algorithm to do this, and it's probabilistic. It's a randomized algorithm. So it sometimes makes mistakes, but very infrequently. So in the process of running this algorithm, you flip coins, and it tells you almost certainly with probability very close to 1, whether this number n is prime or not prime. And this is the basis of cryptography, of the RSA crypto system. What the RSA crypto system relies on is, it's very easy to tell whether n is a prime. But if I give you n, which is not a prime, so if it's, say, a product of two primes, p and q, and I ask you to factor n, that's a very hard problem. We do not know how to do this in less than exponential amount of time. So that's the basis of cryptography, like RSA crypto system. And then turns out there's a quantum algorithm that allows you to quickly factorize n in a number of steps which grows only polynomially in the length of n. So this is one of the key algorithms, key quantum algorithms, and that's one of the key applications to break cryptography. Okay, so we'll, over the course of this semester, we'll talk about all of these problems and many more. Okay, so I think we are running out of time, but if there are any quick questions, please.
Just want to share that the video quality was significantly improved in the last segment. So.
Oh, really? Oh, great. Uh-huh. So maybe there's some playing to do with these settings, and it's not clear to me why the video quality should be worse while playing a video than just in Zoom, but maybe there's a matter of figuring this out. I do have a yeah. So possibly you know, I can imagine that. So first of all, are there any questions and about either what I covered or about anything else about the course?
Oh yeah, do you recommend reading the textbook before lecture and actually doing the problems at the end?
Yeah, do I recommend reading the textbook before the lecture? Well, you know, I think people learn in many different ways. You know, some people like to learn best by reading, and that you know, then you definitely should do that. And I think generally, I would imagine many people can benefit from it. Some people benefit from watching or hearing about something, and then, you know, if that's your style, that might be better for you. So I think that's something that you should figure out for yourself. But I can imagine that there are many people for whom this would be helpful. There's one other thing I should sort of say. You know, there's something we'd like to emphasize during this course, which is what we are trying to teach is not the hard stuff. You know, it's going to be conceptually interesting. It's going to challenge you, but it's, as far as possible, we won't teach you complicated things, right? So if you find yourself, you know, if you look at it and it seems so complicated, maybe there's something wrong. Or if you give you a homework problem and it seems so complicated, well, maybe you already went down the wrong path, right? So this is something that you should really hold. You know, this is something a thought you should really try to hold on to. You know, we are trying our best to make sure that we are presenting you with concepts that are really interesting, important. You know, they are powerful, but they are not complicated.
All right, thank you so much, Professor.
Any other questions?
Oh, yeah. Should we go and finish the second lecture video that we skipped over, like the last part of it?
Sure. Yes, absolutely. If you, yeah.
All right. Thank you.
So Professor.
Yes.
Yeah. So do you recommend us to go over the big O notation that we sort of?
Yeah, that would be a good idea. It was just a little bit of review of big O notation. I think it's something you'll go over anyway in section or in homework. So it was just a little bit of, I'm assuming you've all seen big O notation, and it was just trying to make sure that
thank you.
You swapped it back into mind. Okay, great. Well, thank you very much. Good to see you guys, and see you on Tuesday.
Professor?
Yes.
Do you mind I ask a rather technical question?
Okay.
So regarding your, so in the first video that in that you said that the Fibonacci numbers is always greater or equal to 2 to the power of n divided by 2 minus 1.
Mm-hmm.
I was trying to prove that if I do a strong induction, it's not very difficult, but in that way I don't get any intuition of why you have that lower bound. So I'm wondering if you have any intuitions.
Why is it that way? Well, you know, you're sort of doubling, right? You know, your next number is the sum of the previous two, so you're sort of doubling, but you're doubling at half the rate, right? So if you lag by 2, and then you're saying, well, you know, it's you know, if every time you double a number, then you know, the nth number would be 2 to the n. But it's every other time you're doubling, because you it's not that going from n to n+1, it doubles. Going from n to n+2, it more than doubles. So that's why it's more than 2 to the n/2.
Yeah, I see.
Yeah.
Thank you.
Okay, great. See you all. Oh, okay. So maybe we can, Iman, do you want to talk after this? So maybe we can, should we set up a?
Yeah, we could do a separate call as well.
Yeah.
Oh, you should stop recording actually.
Yeah.